Okay, so first thing is just graphing the inequalities. What's the difference when you guys graph an inequality versus an equation? You guys have done this in the world of lines before. You graph lines, and then you've graphed linear inequalities. And what's the difference in what you see on the graph, Alex? Good. Good. There's like shading. So normally when you're graphing an equation, you're saying this x makes this y, right? This y, this is what we get for y when we plug this x into this thing that makes it equal. And that's why you get all the points on one line or on one parabola. Those are all the points. You plug in that x, it makes that y. You plug in that x, it makes that y. But when you change it to an inequality, you want to plug in an x, and it doesn't have to make a certain y. It just has to make a value bigger than that y. So you want to know what that y is, but you also want to be aware of everything bigger than that kind of idea. So we're going to go ahead and look at how the shading might look a little different here. It's really the same idea. Yeah. Yes, so the lines can be dotted or solid. So for example, we're not going to actually graph part B, but if we were doing part B, this one would have a dashed line as its boundary, because when you're writing these lines or curves on the graph and shading, you're saying these things are the answer. The things I've put on the graph are the answer. Can't express a bunch of points any other way but like by the picture. So when you're saying that's the answer, the dashed line is telling somebody the points stop here at this boundary, but you should not pick points on this boundary because it doesn't actually make the inequality true. Whereas the solid line, like we'll use over here in example A, represents the boundary. The points stop at this boundary, but you should also include points on the boundary because they are the ones where when you plug in this x, you get something exactly equal to that y. And so this equation has, or this inequality has the equal to, so that's why we'll have the solid boundary, whereas this one doesn't, so it's just acting as a boundary, but we can't actually include the points where they're equivalent on both sides. Like 0 is less than 0 is not true. But 0 is less than or equal to 0 is true. And so that's the difference between including and not including it. Okay? So our boundary for part A is going to be solid. And the first thing we would do is we would just graph it like we would graph a quadratic. So quick graphing review for you guys, right? If this said basically y equals negative x squared minus 6x plus 2, what is our strategy for getting a nice graph of this quadratic equation? Chris? So in standard form, we want to start by finding that axis of symmetry, okay, to help us find the vertex point, and that's at negative b over 2a, which in this case ends up being calculated like this and gives us negative 3. Okay. So the axis of symmetry is at x equals negative 3, and that's the x coordinate of our vertex. To find the y coordinate of our vertex, we will have to plug in negative 3. And so that gives us 11. So our vertex point is going to be at negative 3, 11. Okay? I'm going to plot that point. So what else do we do after we get the vertex point and where the axis of symmetry are in standard form to get the graph of the equation? Ariane? Y-intercept. Good. So we can actually plug in any point we want. In this case, the y-intercept's easy to find, and it's not too far from the axis of symmetry, so it's a good choice. If we plug in 0 for x, we get 2 for y. So we know that the y-intercept is at the point 0, 2. And then we also know there's a point symmetrical on the other side of the axis of symmetry with that. So that point was 3 away horizontally on the right. I'm going to draw the same point 3 away on the left side. And then I have some points that I can graph the parabola. And again, this one is a solid graph because our inequality says equal to. So I'm going to go ahead and graph, sorry if I can draw straight lines, my quadratic. Okay. So this is just a boundary. You guys are pretty good with lines. So when you guys graph lines, let me make it a different color. You guys are pretty good at understanding When you draw this line across your graph here, it splits it into these two sections of the graph. And if you're looking for the points that make the inequality true, that it's less or greater than those values, that those exist on one side of that line, and you guys have some different methods for figuring out which side then works or has the solutions. When we're now looking at quadratics, it's the exact same idea. It's just that the boundary has been bent, okay? It's a weird shaped boundary. It's not linear. So when we look at a quadratic like this, it still is dividing our graph into two sections, okay? One section that's kind of all within the curve of the parabola right here, and then another section that would contain all this area that is beyond the curve over there. Does that make sense to everybody? So there's still two sections of the graph because there's one continuous boundary. They're just in different shapes than you're used to. So the same strategies that worked for you here work for you with lines can work for you here. So what are some ways that you knew which direction to shade when you were working with linear inequalities? How do we know where to shade? Kristen?
In the equation, if it says y is less than, then you're going to choose the side that has less than.
Good. So if we read the equation, it says we want to have solutions where y is less than this boundary that we've graphed and created. That means if you pick like a point on the graph, think about where the y's would be less than the y value of that point. Oh, sorry. And that would be down here, right? If I pick another point, where would the y's be less than this? Down here. Where would they be less than this point? Down here. So that makes me feel like my shading should be in here. Okay? What's another method that you guys have? Ariane? You can plug in a point. Yeah. So like, let's say 0, 0 still makes it because it hits right there. So 0, 0 is just such a nice point, right? If I can, I always want to plug it in. So I'm going to plug in 0, 0. If Kristen's theory is true, right, we can shade the direction that the inequality is telling us. 0, 0 seems to be included in the solution. So I'm thinking that that's going to be true. If you don't get Kristen's idea, then this would just be your initial idea would be to plug this in and see what happens. So when we plug in 0, 0, we get this for the inequality. I plug in 0 for y and 0 for x. So I get 0 on this side, 2 on this side, and the inequality reads 0 is less than or equal to 2. True or false? True. Okay? So 0, 0 is a solution to this inequality, which means that point in that position is in the region where our solutions lie. So we definitely have shading here. Okay? So this would be our shaded region, everything on that side of the parabola boundary. So we just plugged in anything we wanted, Matt. And in this case, it was easiest to plug in 0 to get the y-intercept. So in standard form, when we plug in 0, those just basically become 0. So we got 2 for y, so we plotted 0, 2, and then we just reflected it on the other side of the axis of symmetry. Okay? And again, you guys don't have to plug in 0. You could plug in anything that's not too far from 3 so that it's not crazy, like off your graph and your scale. But 0 is pretty friendly. Okay? Are we okay with graphing the inequalities? Okay, so now what we're going to do is we're going to solve the inequalities. And I want you guys to remember what solutions were. When we were graphing an equation, okay, which part of the parabola were the solutions when we looked at the graph? I see Chris and I see Alex, they both, and Chris, they all gave me some. Jason. Good, the x-intercepts. These were the solutions. These were the only place that the graph crossed and made exactly equal to 0, and our equation was about being equal to 0. The inequality is not about being equal to 0. It's going to be about being less than or greater than 0, which means there's not just going to be two places that could possibly be solutions. There can be a whole bunch of x's that can create things that are less than 0, or a whole bunch of x's that could create things that are bigger than 0. Okay, so difference between equation and inequality. Okay, so we're going to go ahead and look at the examples below this and do some of the inequalities. We are going to skip the calculator ones. And so we're going to start with these ones. We're going to look at part A and part B. Our expectation is that you'll do this by hand, okay? So the solutions are still important, like the x-intercepts, but we'll see they provide something different for us than the answer. They just provide us a way to start looking for the answer now, okay? So this inequality, this is a quadratic inequality because if I multiplied these out on this side, I have a quadratic, okay? And it's saying that we want that to be less than 0, okay? So I'm supposed to figure out what x's, when you plug them in here, they create numbers that are smaller than 0, okay? Now think about your parabola for a minute and its shape. If we were looking at a picture and I told you, I want you to tell me which x's are making something that's less than 0 when you plug them into the equation, think about this x. So here's an x value on the x-axis. That x corresponds to this point on the graph. So when you plug this x value into the equation, did it make a positive or a negative outcome when you plugged it in? Positive, because it ended up being plotted at this point, which meant when I plugged in this x, I got some positive y value from my calculation, which made me plot here. Okay? What about right here? When I plugged in that x value, what outcome did I get? 0. That's why it's on the x-axis. What about for this x right here? When I plugged this x into the equation, I ended up plotting this point. So when I plugged that x value, I was getting negative results. Is this idea okay with everybody? That like you're finding an x, but x had something done to it. You plugged it in, you did some calculation, and you're looking at what the calculation looks like when it's done. Okay? So here's the interesting part. Even though we're not solving and looking for the zeros anymore, the zeros are of information. Because notice, where are all of the x's in this picture that gave negative answers when we plugged them in and did the calculations? In other words, the x's that gave us negative y values, right? Yeah, in this case, they were between the solutions, right? All of these x's turned out to give us negatives. And then where are the ones that gave us positive results? Outside of the zeros. Now, a parabola has this distinct shape to it, right? So it might not be every time that the ones in here are giving you the negatives, because the parabola could go the other way. But do you see, even if it went the other way, the x's in here are giving you one kind of result, and the x's out here are giving you a different kind of result. That those zeros might not be our answers anymore, but they're dividing up our graph into the x's that give us one kind of answer and the x's that give us a different kind of answer. Is that okay with everybody? So what we're going to do is we're going to try and use that idea to our advantage. I know 4 and negative 7 are not the answers to this problem. They would be an answer to the problem if it says equals 0. And if you write 4 and negative 7, I will give you no credit. Okay? I'm not trying to be ridiculous, but this is a completely different idea than what we were doing before with an equation, right? So if you just write the answer to an equation, you're not considering that this is actually an inequality and it's a little different. Okay? However, 4 and negative 7 are really important in me analyzing my solution, because I understand that because those are the zeros, that they are splitting up the parabola into these sections where if I plug the numbers in this area, I'll get one kind of result, but if I go on the other side of the zero and plug in these numbers, I'll get a different kind of result. Is that okay with everybody? So I want them there so that I can kind of analyze what's happening, but they're not necessarily part of my solution. To decide if they're part of my answer, I have to look here. 4 and negative 7 are the values of x that make this equal to 0. Is being equal to 0 part of the solution of this inequality? No. So these are really important points for me to look at, but I do not want to include them in my solution. So if I were going to mark them on the number line, I mark them with open points, telling myself these are super pivotal. I want to look at each side of them, but I don't want to include them because it didn't say I could be equal to 0 in this inequality. Okay? And now what I'm going to do is I'm going to explore what's happening like we did right here. But I'm just going to do it numerically. Okay, so there's a way for us to do it graphically and also a way for us to do it numerically. If I plug in the x's that are smaller than negative 7, so everybody think in your head of an x that is smaller than negative 7. Okay? When you take that number and subtract 4, do you get a negative or a positive? A negative, no matter which one it is. I didn't tell you guys to share your number, right? But anything that's smaller than negative 7, negative 8, negative 9, negative 10, negative 11, when you subtract 4, you're still going to get a negative. Now take your number that's still smaller than negative 7 and add 7 to it. Do you get a negative or a positive? Still a negative. It doesn't matter. Yours could be negative 10. Mine could be negative 7.1. But when we add 7 to it, we're still going to get a negative, and a negative times a negative will end up making a positive. Now you guys can find the exact value if you want. I'm not, because I know I'm just comparing it to 0, and I don't want to do all the extra arithmetic. I don't want to actually have to multiply all these things out and stuff like that, especially if the boundaries are like at halves or something like that. Okay. Now pick a number between negative 7 and 4. Okay. And we're going to look at the same thing. If the number is between negative 7 and 4 and you subtract 4, what do you get? Negative still. What about if the number is between negative 7 and 4 and you add 7 to it? You get a positive. Okay? And that negative times that positive will make a negative. Okay? Now everybody pick a number bigger than 4. Okay? To represent the x's over here. Okay? When you take your number that's bigger than 4 and you subtract 4, do you get a positive or a negative? Positive. And your number bigger than 4 plus 7 will give you positive. And the positive times the positive will make a positive. So this is just kind of, we call this a sign analysis. We use this a couple of different places when we want to understand if when we plug in certain x's, we're getting positives or negatives without having to actually like plot a bunch of points or do a bunch of calculations, okay? So this tells me these x's make this thing positive, these ones make this calculation negative, and these ones make the calculation positive again, okay? But what's the answer to the problem? What does the inequality say? I want this thing on the left side to be less than 0. What kind of numbers are less than 0? Negative numbers. So in other words, this is going to be true or correct when I get a negative on this side for this calculation. Okay, so look at your little analysis. Which x's made this calculation over here come out to be a negative? In between here, right? These x's make that calculation come out to be a negative. So in other words, my answer is that x has to be bigger than negative 7, but at the same time, less than 4. In other words, all of the x values or numbers that are between negative 7 and 4 are the answers to this problem because they are the numbers that make that calculation come out to be a negative, which would be less than 0. Is this okay with everybody? We're going to do it a couple more times, but do we get the general idea of what's happening? Okay, so number one thing to do wrong. Write down x equals negative 7 and 4. Miss Doll will cry while she grades your paper. You'll see little wet spots from me wiping my tears. Okay, and I'll put it away because this is not an equation. This is an inequality. There's more happening there, okay? Second major thing to do wrong. Recognize that it's an inequality, but totally not be willing to do any of this analysis right here. And so you get negative 7 and 4 and you just put them together in some random way with these symbols. Okay? So don't do that either. So there's not a lot of like written work to do here, but there's a lot of thinking work to think about how this is happening. Okay? And you can do the thinking numerically like we just did. You can also do it graphically pretty quickly. If this is a quadratic, if you were graphing y equals this, okay, we have it all written on this side. Y equals this. Would this parabola face up or down? Up, because the lead coefficient would be positive, right? Think about it. You can see all the x's that gave us a positive, all the x's that gave us a negative, all the x's that gave us a positive by just thinking about the shape of the graph like we did over here. Or, if you like the numerical approach, you can plug in the numbers. But you're not really going to understand what the solutions are unless you actually do some analysis because the parabola can be flipped multiple ways. It could actually not touch the x-axis at all. Okay? What if it didn't touch the x-axis at all? Okay? What if it didn't factor and it was some quadratic that had no real solutions? We're in a world of hurt. But think about it. Here's your x-axis, and let's say your parabola was up here. So either the answer is every x makes what we want, or none of the x's do, right? Because every x that you plug in is going to give you what kind of answer for this parabola? A positive. So if it had the parabola equation and said, when is it greater than 0? I would say all the time. Every x gives me something greater. If it said when how would I figure out that numerically? I would just a number, there's nothing dividing up my x-axis essentially, right? There's no real intercepts where it might change from being positive to negative. You just pick the number, plug it in, and see what happens. But there's only one thing that's happening. So it's actually less work than over here because there's not like different distinct sections that work out a different way. It's like everything works out one way. So if you can't factor it or get anything that crosses the axis, don't worry. Okay, it just means everything falls into one category and you just have to plug in a number and see which category they fall into, kind of true or false. Is it going to make it work or no? Okay. All right, so we are going to we're actually going to skip part B. It's really similar to this one. The only thing is like the equal to part. And we're going to look at part C, okay, and then some of the try these ones because they have some unique situations. So let me get part C up here for those of you that don't have the note guide. Go like this. Okay. So we're going to look at part C. I'm going to have you guys go through it and try it. Just remember that when you're working on one like this, we don't really want to compare it to 4. Okay? 4 is not nice for us because then it doesn't correspond with the graph, how like the intercepts really split it up to the x's that will be above and below. That only works when we're comparing it to 0. So if we want to use all the ideas and patterns that we've seen so far, it has to be compared to 0, not 4. So the first thing that we would want to do is just read so that the 4 is on the same side. See inequality. Okay, and then we'd want to go from there. So go ahead and in your groups, try to see if you guys can solve this inequality on your own. Okay, so did you guys factor? Okay, so it was factorable. If it wasn't factorable, you guys realize you can still find the solutions, right? What would you do if it wasn't factorable? Complete the square, use the quadratic formula, and find the solutions. They won't be as nice, okay? They'd be horrible numbers, right? Because it wasn't factorable. However, you don't have to pick that number to plug in, right? You just have to pick something on one side of it or another side. So you would just pick numbers that were nicer to use than those horrible numbers you got, and you just wouldn't be able to plug into the factored form. You'd have to plug it straight into the standard form, okay? So what did you guys get as factors?
3s plus 4
sorry. 3s plus 4. Sorry, you guys, it like won't write. And 2s minus 1?
Yeah.
Okay, so then negative 4/3 and 1/2 would be your solutions if it was an equation. So those are kind of our points where we want to analyze what's happening. And if you guys plugged it in correctly or analyzed graphically what was happening, you should have gotten this kind of idea. Okay? So pick a number in those realms, plug them in if you're uncertain. Okay, and that's what we could get. And then what am I going to choose as my solution here? Haley? Okay, so are you picking the center part here or the parts on the outside? The parts on the outside, good. So, and then do we want to include the endpoints or no?
Yeah.
The solution, no, because weren't included, right? But we want positives, right? We want things greater than 0, so we'll pick these. So this is a little bit tricky. You guys cannot write the answer in the same format we did before. It is inequalities, but you can't write it as one of those sandwiched inequalities. Those ones with x in the middle mean x is doing both those things at the same time. So in the last one, when we compared s to the two different numbers, -7 and 4, and we put x between them and said x was greater than -7 and less than 4, the way you wrote that isn't just like a way to write it. It's literally being read as x has to meet both those requirements at the same time. S, in this case, cannot be over here and over here at the same time, so we have to write it with some different format. If we set each of these equal to 0. So if I set 3s plus 4 equal to 0, I get -4/3, and 2s minus 1 equal to 0, I get 1/2. And so the way we'd want to write this solution is that x is less than -4/3, or x is greater than 1/2. The reason, again, I can't write this as like a sandwiched inequality, okay, is one, Their signs would be kind of weird in there. And then if I did write them in the correct format, it would be trying to tell someone that x had to be smaller than negative 4/3 and bigger than 1/2 at the same time, which is an impossible type of idea. So when it's not a cohesive segment that you're trying to write it as, you have to write it as two separate inequalities. Okay? Is this all right with everybody? Okay, so the last idea I want to discuss here is when it works out slightly differently. So if you look at the try this part A, if we rewrote that, it would look like this. What does this factor as? D squared plus 8D plus 16. Yeah, D plus 4 and D plus 4, right? So we're getting D plus 4 squared. It's a perfect square. How does that make it different from the situations that we looked at previously? Yeah, there's only one solution, but that's okay. That just means less areas for us to look at. We can still do this same analysis. It just means the only place where it's equal to 0, in this case, is at negative 4. And I'll include that point because I do want it to be equal to 0. And then I can either think of the graph or plug in numbers. So when you plug in a number smaller than negative 4, you're going to get something in here, and then you're going to square it. So will it end up being positive or negative? Positive. The last thing you're doing is squaring it. So it doesn't even matter what happens here. Once you square it, it becomes positive. And same thing on the other side, right? It's always going to become positive because of the squaring. And in this instance, we're trying to find things where this value ends up being greater than or equal to 0. In other words, positive, which it's equal to 0 here, and it's greater than 0 for all of these D values. Okay? So all real numbers because my entire number line is filled in. Okay. And there could have been a little bit of changes to this problem that would make it slightly different. So I'm going to write some things on here that are not for you to copy down in your notes, but just to think about for a minute. Let's say I took off the equal to. How would that change the solution that we just got? Let's see, Chris. Matt. Good. It would be all real numbers except for negative 4, where I'd have this one place that it wasn't filled in. Okay? What if I took the equal to sign off and I turned it around this way? So I just wanted that quantity to be less than 0. Not equal to, just less than. There would be no real solutions. Is that okay with everybody? Okay. What if I said it could be less than or equal to? Then we would just get negative 4. Okay, so it could work out a couple different ways, okay, especially in this case or the case where you have nothing for it to hit on the axis, okay, but the analysis should still work no matter what you're doing, but you have to trust that you have the confidence to get through the analysis and that you understand what's happening in the problem, all right? So this is how you guys are going to go about solving the quadratic inequalities, okay? So yesterday, did you guys get to do any of the Skill 8 homework? Yeah? Okay. So that was yesterday's homework, okay? If you haven't done it, go and do it. And then tonight's homework on solving inequalities like this would be Skill 9 homework, okay? There's one more lesson tomorrow, but 2 more skills. That's because tomorrow's focus is on systems, okay? And there are systems of equations, and then there are systems of inequalities, okay? So you've done systems before. The difference now is that some of the equations will be quadratic. They're just 2. Okay. But the systems include quadratics now instead of all linear stuff. No.
I can see it too.